Hello, this is Mr. Gilmore with the 7.4 Side Angle Side and Side 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 Similarity lesson. Now, we are going to skip the proofs for these two theorems. As it turns out, they're nearly identical to the proof of the angle-angle similarity. What we would do is construct a third triangle such that it's similar to the first and congruent to the second, and then using our similarity congruence conductivity theorem, we could prove that the first and third are in fact similar to each other. So in my best Yoda voice, the proofs, for go we will, nearly identical to the proof of angle-angle similarity. They are. So let's jump right into what is the side-angle-side similarity. We'll read this now, and then we'll also read through side-side-side similarity later. So SAS similarity, or for shorthand for us, you can just write SAS and then the similar sign behind it. We need to know, what does the side angle side similarity state, right? This is a theorem, so it's in conditional form. And just like any conditional form, we must be able to satisfy the given in order to reach the conclusion. So let's read what this says. If two sides of one triangle are proportional to two sides of another, and the included angle of the first equals the included angle of the second, then the triangles are in fact similar. Let's illustrate this. So if, right, let's say we have these two triangles, ABC and RST. If we know that two sides of one triangle are proportional to two sides of another, in other words, AB over RS is equal to BC over ST, and we know the included angles, right, because we're working with the angles that are sandwiched between our proportional sides, then we may conclude that these two triangles are in fact similar. Now, remember what similarity is, what these triangle similarity principles are. They're very much like the principles of congruence that we saw way back in chapter 3. These are shortcuts to similarity. So we have now two shortcuts on our list. We've got angle-angle similarity, and now we've added side angle side similarity, which we'll see some examples of using side angle side similarity later on today's lesson. Okay, so then what follows from similarity, right, the shortcut to similarity? Well, what it follows immediately is, well, we start off with three things, right? We had a pair of included equal angles, that was one thing, and then we had a pair of proportional sides. That's really our two things, right? Two sides of one triangle are proportional to two sides of another. So now that we have those three things given to us, we can determine, since these two triangles are in fact similar, we determine what we know about the rest of our triangles, right? If we know that the first pairs of sides were proportional, that means the third pair of sides is also going to be proportional. So in our diagram below, we know that AB is ratio to RS. So then what is something else we can then conclude, or what follows about this? We know the third pair of sides, AC and RT, those are also proportional to the other sides of our triangle. So we now know that all three sides, right, all three corresponding sides of our triangles here are in fact proportional. It also follows that our corresponding angles, right, are equal. We can then conclude that angle A and angle R are going to be equal. Those are corresponding. And we can conclude that angle C and angle T are equal, right? This is all, right? We actually get all three of these pieces of information because of the definition of similarity, right? If we can prove the triangles to be similar by side angle side similarity, then we know more information about those triangles based on what it means for the definition, right? By the definition of similarity, we know that all sides must be proportional, and we know that all corresponding angles must then be equal. So again, it's just like we saw back in chapter 3 with congruence. Congruence gives us more information. It's a shortcut, right? Same thing happens with similarity. It's a shortcut into more information. Now, what this leads us into then is one of our theorems that we can actually prove very easily with the side angle side similarity. It's called the triangle midsegment theorem. Before we get to that, let me help you define what is a triangle midsegment. So a triangle midsegment is a segment whose endpoints are the midpoints of two sides of a triangle. In other words, given any triangle, pick two sides. Okay, so you pick two sides of a triangle, mark their midpoints. In our diagram below here, DE is in fact a midsegment. D is the midpoint of segment AB, and E is the midpoint of BE or BC. When you connect point D to E, you're connecting the midpoints of two sides of a triangle. That's a triangle midsegment. Now, some of you guys have seen this definition already. This was something that I did first semester with triangle midsegment, and this leads into now a triangle midsegment theorem. Okay, now some of you guys have already seen this one. In first semester when we tackled triangle midsegment theorem, it was a little bit trickier because we were using congruence and our properties of parallels and our properties of parallelograms to arrive to our conclusion. But now we have another theorem that helps us tackle the triangle midsegment theorem much easier. So let me introduce you to the triangle midsegment theorem. Here's what it says. A triangle midsegment actually does two things in a triangle. It is parallel to and half of the length of the side that it does not intersect. So in our diagram here, if we're given triangle ABC such that DE is our midsegment, we're going to prove two things about segment DE. The first thing is that DE is parallel to AC. So in other words, we can prove that DE and AC will be parallel to each other. But the second thing we can prove about DE is about its measure. It's actually equal to half the length of AC. In other words, if we know, if we were to say that the length of DE is x, then the length of AC would be 2x because DE is half the length of AC. Now, we're not going to go through the proof of this here in the lesson slides or in this video. I'm going to leave this for you guys on the worksheet, and on the worksheet, I'm going to guide you through this. So I have the two-column proof already typed up for you. It has all the statements already filled in. You're going to help me fill in the reasons. All right, and proving this is very simple now because we have a new way of proving similarity. Right, similarity is a very powerful tool. We have side angle side similarity. So a little bit of a heads up when you jump into this theorem, you will use side angle side similarity to help you prove that these two triangles are similar, and then that helps you arrive to your conclusions that the segments are parallel and that DE would be half the length of AC. All right, now let's move on to our second similarity statement, our second similarity principle today of side-side similarity. So this one states, if the three sides of one triangle are proportional to the three sides of another, then those triangles are in fact similar to each other. So again, it's a similarity shortcut. All we need to know is the three sides of one are proportional to three sides of another triangle. We've got ourselves then similar triangles. This then finishes off all three of our triangle similarity principles. We have angle similarity, side similarity, and this last one, side similarity. Here's a quick illustration of what this looks like. Again, we're given two triangles, ABC, RST, and we're given that the three sides of ABC, so AB, BC, and AC, are proportional to the three sides of our second triangle, RS, ST, and RT. And so we're given that all three sides are proportional, then we can conclude the triangles are in fact similar. So just like we asked before about, well, what follows from our shortcut? So what would follow from our side similarity? Well, then our angles, right? What do we know about our angles? This would imply that if we can prove that two triangles are in fact similar by side similarity, then we conclude that all the corresponding angles are in fact equal. Okay, so we match up our corresponding angles, we can claim them equal. Why can we claim them equal? Because by definition, we have similar triangles. So by definition of similarity, we have all sides proportional, and we have all angles equal, or all corresponding angles equal. So here's what the last several slides of our lesson are going to look like. We're going to practice using our side angle side, our side similarity, and also pair it with our last lesson similarity, angle similarity. What I'm going to do is I'm going to give you a diagram with two triangles in it, just like we did in our last lesson with angle similarity. But now we have three tools. So I'm going to give you two triangles. And with those two triangles, you're going to determine first, are they similar? Meaning, can you use one of the three triangle similarity shortcuts to show that those two triangles are in fact similar? And once we determine if they are similar, then I'm going to have you write a similarity statement. If they're not similar, we're not able to determine that, then we'll just skip the similarity statement altogether. So let's take a look at our first example here in slide 10 here. So are these two triangles similar? Well, I'm going to go ahead and answer this for you. It is yes. Okay, these two triangles are similar. But now you're going to help me figure out why are they similar. Let's take a look at what we have going on in our diagram. First off, right, I'm looking to satisfy one of our similarity shortcuts. So first off, I'm seeing that I have a pair of equal angles here. Vertical angles jump right out at me, which means I already know that one pair of angles of one triangle are equal to an angle of another. If I could find a second pair of equal angles, then I've got myself angle similarity. But there's not really much going on left in our diagram that kind of tells me about our another pair of equal angles. but I do have side measures here. So notice that with the side measures given, I'm wondering then if I can determine that two sides of one triangle are proportional to two sides of another. So I'm going to test this. I'm going to test the sides. So what I can do is I'm going to pick one side of a triangle and I'm going to ratio it with the other. And then I'm going to create a second ratio using my other pair of sides and determine, can I find that those sides are in fact proportional, meaning they form the same value of ratio. So my first reaction was to say, hey, let's take 10 and ratio it with 22. So if I had 10 over 22, then I would check that with versus 11 over 20. Well, 11 over 20 doesn't reduce, but 10 over 22 does reduce to 5 over 11. Well, as it turns out, are those proportional? No, okay? But is there a second way that I could have created a ratio of these? And there is. Instead of matching 10 to 22, let's match 10 to 20, okay? What if I made a ratio of 10 to 20? So those didn't work. So let's make it 10 to 20. So going from my small side to my large side, 10 to 20, let's do that again with my second pair of sides here, 11 and 22. Now the question is, do those form the same ratio? If I reduce, take a look, 10 and 20 reduce to a half, 11 and 22 reduce to a half. Yes, these are in fact the same ratio. So what am I really saying there? I'm saying that that two sides of one triangle are proportional to two sides of another. And I have the angle sandwiched between those pairs of sides. So what do I have going on here? I have side angle side similarity. So yes, the two triangles are in fact similar. By side angle side similarity, I can prove that with my proportional sides and my included angles being equal. So now I need to write a triangle similarity statement. I'm going to start with W in the middle. I'm going to go WTZ, traveling along my side 10 there, and that's going to be similar to then W corresponding with itself, WYX. And there we have it, a similarity statement showing that, yes, again, we know these triangles will be similar. Why? By side angle side similarity, and I've matched up my corresponding parts in my similarity statement. Let's do another one. Okay, in the diagram, there are two triangles, triangle AEF and triangle ACB. I'm going to determine, are these two triangles similar? Well, I'm going to go ahead and give this away. Yes, they are. Okay, those two triangles are similar. But why are they similar? Was it by side, 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 angle, angle, or side, angle, side similarity? Which one of those three? Well, immediately I recognize that two triangles overlap and they share a common angle. So I already know that one angle of one triangle is equal to one angle of another. If I'm going to find a second pair of angles, I can claim angle-angle similarity. However, again, I'm not dealing with any other angle relationships, so I've got to cross that one off my list. Let's see. They've given me some information about some segment values, segment lengths. I know that AE is 8 and AF is 10. And they also gave me EC is 4 and FB is 5. Well, what you'll notice then is that I need to know, if I'm going to find proportional sides, I need to know the entire length of these sides. So I'm going to take 8 and add it to 4. 8 plus 4 gives me an entire length of 12. Let's do the same thing for side AB. I'm going to add my two lengths together to get the entire length of AB. So now let's check. I'm going to then form a ratio of my smaller side triangle to my larger side triangle and see if these ratios are actually proportional to each other. So I'm going to start with this side 8, and I'm going to ratio it with its corresponding side 12. Okay, all right, 8 is the small part of the small triangle, 12 is the entire triangle, the bigger triangle, 12. Let's test that against the other pair of sides, 10, which is the segment of the smaller triangle, ratioed with 15, the length of the larger side of the triangle. The question is, are these the same ratio? Because if they are, then we have proportional sides. So 8 over 12 actually does simplify that, where you could divide 4 out of both of those. That gives us 2/3. And 10/15, 5 divides in both of those, giving us 2/3. Hey, hey, we do have two sides of one triangle proportional to sides of the other. I don't know anything about my third sides, but I do have my included angles being equal, right? Angle A is equal to itself. So there we have it. I'm using side angle side similarity again, and I can write out a similarity statement. In this case, I'm going to go triangle ABC. I'm going to start there. Triangle ABC. So my larger triangle is in fact similar to my smaller triangle. That would be AFE. Is that correct? Yes, ABC. B and F correspond. E and C correspond. Very good. So triangle ABC, triangle AFE. Very good. So again, you're going to see some questions like this on the worksheet where I'm going to give you two triangles. You determine by which method are they similar, if they are similar. Okay. Of course, they don't have to necessarily be similar. In this case, yes, they are by side angle side similarity. let's keep going. Let's do another example. In the triangle below, in the diagram below, we have two triangles, ABC and EDC. The question is, are they similar? Well, yes. This is going to be a quick example here. Here's why. I already notice, okay, that the two triangles have right angles in each. Angle B and angle EDC are both right angles, which means I already know by our right angle theorem that if I have right angles, they're all equal. So I know that I have one angle of one triangle equal to one angle of another. But take a look at our two triangles again, ABC and EDC. They both share angle C, which means we have a second pair of angles. I know I have my pair of right angles, and angle C is a reflexive angle. It's shared, which means bingo, we've got angle-angle similarity right off the bat. These two triangles are in fact similar by angle-angle, which means I can write out a similarity statement. I don't have to check any sides. I automatically know I have got some similarity between these two triangles by our angle-angle similarity. So I'm going to say triangle ABC, and that's going to be similar to triangle EDC. So B and D correspond, A and E correspond, and C correspond with itself. Okay, almost finished. Let's do a couple more examples. So, question is, in this diagram below, we have triangle ABC and triangle RBS. Are the triangles actually similar? Well, again, they are, yes. And I could go through the nitty-gritty of this. Okay, I go through the showing this again, but these are similar, and I can already know they're similar because this RS is a midsegment, and because it's a midsegment, we can use side angle side similarity. We can prove that these two triangles are in fact similar, but we can take this a step further. My question now is, if these are similar, could we find the missing variable in this diagram? We know the length of RS is 3.9. Could you tell me what the length of AC is? And yes, you can. Remember, RS is a mid-segment. We have a new theorem this lesson, the triangle mid-segment theorem. It says two things. The first thing is that RS is parallel to AC. That's the first thing it says. Okay, but the second thing it says is that RS is equal to a half of the length of AC. That means RS is 3.9. I can then use that value to figure out what AC is. If RS is half of AC, that means AC is twice the length of RS. In other words, to figure out the length of AC, I'm going to take our length 3.9 and just double it, multiply by 2. We get 7.8. And that 7.8 is in fact the length of our missing value of AC. That is our X value. And that is using our theorem we saw this chapter, the triangle mid-segment theorem, just a few slides ago. And we can prove that again using side angle side similarity. And of course, you'll prove that on the worksheet. But here, very quick example of finding a missing variable using the triangle mid-segment theorem. I know RS, which means just double it to get AC. I could work backward. Let's say if I gave you AC, you could work backward to figure out what RS is, again using the same theorem, triangle mid-segment theorem. Okay, you made it. This is our last example. Last example is a little bit trickier. Okay, the first question is, are these two triangles in the diagram similar? I see triangle ABC and triangle AED. And the answer is yes. I can show very quickly that these two triangles are in fact similar. How? Well, because I see the right angles already. Angle DEA and angle C are right, which means I know they're equal. And the two triangles share angle A. So yes, by angle-angle similarity, these two triangles are similar. But what they're asking us to do again is find a missing variable. Here's what's going to help. What's going to help you is write out the similarity statement first, because it's going to help you match up corresponding parts. We're looking for this little segment AE. Well, I need to know what AE corresponds with. Because I know my sides are proportional, I can use my proportional sides, set up a proportion with X in it, solve the equation for X. But in order to get to that proportion, I'm going to use my similarity statement to help me. So I'm going to write this triangle ABC. So that's triangle, I'm starting with angle A, going to my non-right angle B, to my right angle C, is similar to, well then our second similar statement is, I went from angle A to my non-right angle, that's D, to then my right angle, that's E. So notice that B and D are actually going to be corresponding angles. These two angles here are equal. And then, of course, C and E would correspond at those points because the right angle's there. Now, this is going to help me then form my proportion so that I can match up my corresponding parts. So as it turns out, if I were to look at this similar statement, I can match up some corresponding parts that I know the values of. For example, I know what the value of DE is, and it's ratioed. If I look at what DE is, it corresponds to the length of BC. Now, I need to also bring in the length of AE. So I started with my smaller triangle DE, segment DE. So I'm going to do then AE, which is my X value. We'll plug that X in just a second. And it corresponds to another value of another segment of my larger triangle. If I look at my similar segment, AE corresponds with AC. And if you look, I did give you the value of AC. Okay, it's 24. So now we know those values. Let's plug in what we know. DE is a length of 6. BC is a length of 9. AE is our missing variable X, and then AC is the entire length, 24. Now, we have one variable, one equation. We can solve that proportion. Before I do that, I'm going to simplify my life just a little bit by reducing that first ratio. 6/9 reduced to 2/3. Okay, that way I don't have to multiply 24 times 6. So I'm going to do 2 times 24 and 3 times x. I'm going to do my cross products. So 3 times x is 3x. 2 times 24 is 48. And then divide both sides by 3. We get x is equal to 16. And there's our missing variable. Alrighty. So with similarity, we can use similarity, whether it's angle-angle similarity or side-angle side similarity or side-side similarity, as a shortcut to reach more information about our given triangles. Because with similarity, remember those being shortcuts, I can gain access to knowing that all sides are proportional and that all corresponding angles are equal in measure. So on the worksheet, you're going to be putting to use the 3 similarity shortcuts: angle, angle, side, and side, side similarity. You're going to determine if the triangles are in fact similar. You're going to determine why they're similar. So you're going to tell me, is it angle, angle? Is it side, side? Or is it side, angle, side similarity? So please be sure to hop over and take a look at the 7.4 worksheet on side, angle, side, and side similarity. If you do have any questions on that worksheet, do not hesitate to email me. I will get back to you. We are at the end of our lesson, so be good and do good.